Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is a new episode of the podcast Turbulence at the Exascale. So if you're not familiar with the podcast is designed to gather the view of the turbulence community in the UK and also in the world to try to identify the challenges and opportunity associated to exascale computing for the study of turbulent flows. So the podcast is part of the UK initiative called ExCALIBUR, which is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is to deliver research and innovative algorithm development to harness the power of exascale computing. I'm leading a working group on turbulent flows, and this podcast is also connected with the UK Turbulence Consortium. So today I'm very pleased because my guest is Professor Philipp Schlatter from KTH in Sweden. I'm pretty sure a lot of our people who are going to listen to the podcast know Philipp very well, but is the director of the Linné Flow Center, one of the center of excellence in Sweden. His expertise is in direct and large simulation of turbulent flow, computational fluid dynamics, software development, and high performance computing, of course. So good afternoon, Philipp.
Hi.
My first question is for the people who don't know you very well, maybe can you tell us more about your background, where you are coming from, what you have studied, and how did you end up at KTH?
Well, originally I'm from Switzerland, and I studied at the ETH in Zurich. I studied mechanical engineering, and when I was looking for a master thesis, I kind of got interested in going abroad, and then via my professor, I got a contact with Don Henningsson in Sweden, and I thought, well, why not Sweden? Could be interesting. And so I went to Sweden for my master thesis, and I liked it very much. But then somehow, for personal reasons, I wanted to go back to do my PhD. So I did my PhD again in Switzerland, in Zurich at ETH. But then at the postdoc level, I also thought, okay, let's travel again. And I wrote an email to Don, and then somehow it was possible to come back. And now that's already 15 years ago when I came back to Sweden. And in fact, I'm still in the same unit or research unit, I think is the organizational name, with Don. So it seems that I liked it there, and we kind of got well along with each other. So
very good, thank you. And I'm also curious to know, how did you become interested in so you started doing engineers in general, but how did you become interested in turbulence and high performance computing?
I mean, it's originally, actually, I studied mathematics, or I tried to study mathematics. After half a year, I stopped because it was too theoretical for me. And I changed to engineering because I actually wanted to calculate something, a result. But then while doing engineering, at some point I thought, I mean, I still wanted to go back to kind of the most theoretical part of engineering, and that turns out probably to be fluid mechanics. So that was kind of the reason why I got interested in fluids. And of course, computers, I was always interested in those programming, running stuff. And of course, running big simulations in some sense is, interesting, is kind of cool to do. That's how I got started. But of course, then I learned also much more about, computer science and programming and optimizing, and of course, also the physics. But in the end, it was a combination of my interests of computers, of engineering, doing something, reasonable, and getting an interesting result out. So that's, I guess, how I ended up in what I'm doing.
And so you said you've been working at KTH for quite some time, around 15 years. I was wondering, so I guess you really like working at KTH. So I was wondering, what's the best thing about working at KTH?
I think that the KTH, or perhaps that's Sweden in general, one thing that fascinated me was the very not steep hierarchy that one has in Sweden. So it was, even as a master's student at the time, it was possible to talk to the professors and interact with them, discuss the results, and they were interested. So it was very easy to get into contact with people. And also as a postdoc, when I then came back, very quickly one got the responsibility of being, I don't know, director of studies of some center. One could be part of the supervision of other students. So it was a very easy way to get into the academic life. So that's what I liked. It was not at all hierarchical as perhaps it is in other countries. Of course, there is also problems with that system, perhaps, but that's at least what fascinated me. Also, maybe I have to say that I came perhaps at a good time, good time because it was when this Linné Flow Center that you mentioned before was founded, which was, of course, very instrumental to me and some other colleagues which were there at the same time to actually boost our career or the possibilities of doing research. But also that at that time we actually got a computer at KTH. It was in 2008 that we got a Blue Gene L, I think it was at the time, and it turned out that this Blue Gene was bought by a group doing brain research, but it turned out that they were only using it during the day, during weekdays, so from 9 to 5 essentially, and then in the evenings and in the weekends there was just 2,000 cores, standing there. Nobody was using them, and that was perhaps also then the time when we realized, okay, we need to parallelize our codes. We need to make sure that our codes run on 1,000, 2,000 processors, because we had this machine standing there. And then we started to learn about how to do that. At the time, we still did it ourselves, doing MPI calls and reduction operations by hand. So we then parallelized our codes, and it was, for me and I guess many in our group, kind of a revelation that we suddenly could run on 1,000 processors, and the code was 1,000 times faster. And it sounds weird to say that nowadays when we run on 100,000 cores these days, but at the time this was really a big thing. So we could do our our boundary layer simulations at the time over a weekend. It was kind of unthinkable for us before. And of course, I mean, combining all these things together, it really turned out that was why I wanted to stay and kind of continue to develop these capabilities.
So, I mean, KTH was in the news in the last few days. I mean, you mentioned the first supercomputers, but there was a big announcement made that the new supercomputer is going to arrive soon. It's called, I think, Dardel. And so one of the originality of Dardel is that it's going to be AMD based with CPUs and GPUs. So I wanted to ask you, are you happy with this choice of hardware, and what do you think about Dardel?
So, of course, Dardel is not standing there yet, so we couldn't actually run on it. But of course, we were kind of trying out some of these processors and trying to get some expectations on how the machine would be, and actually I think to directly answer your question, I think we're very happy, and I think it's a good machine for CFD, for our applications. So we did some tests on similar systems, mainly the CPU part, and it turns out that this new processor, the AMD processor, is very well suited for CFD. So one number that I maybe can mention is that, I mean, we run on 2 times 64 cores, so one node of this EPIC processor, and we could reach with a smaller model or mini app, not our main code, but kind of a mini app. We could reach on one node around one teraflop of performance, a bit less, but still around there, which of course is quite impressive, quite nice. So for at least the CPU part, I think we're very happy.
Yeah.
The GPU part, of course, that's a challenge, as I guess we all know, and perhaps fear, or maybe not, I don't know. But we also we have, of course, done a lot of work during the last few years on NVIDIA cards. So we have participated in some of these hackathons with NVIDIA. We have transferred a lot of our code to CUDA, some of the kernels. Now, of course, with AMD, yeah, we don't really know yet, because now the programming model is slightly different. So I cannot tell you how well the code would then work on the AMD GPUs, but we have invested quite some time in getting the GPU part running well. And also there, I think we have now a version of the code that actually performs quite well even on GPUs. And I guess in the end, it will be a technicality to move it to OpenMP and HIP or whatever we will then use. But I think in the end, it was a very good decision for us to have this AMD machine. It will be a lot of challenge. It's a new machine, new compilers and all of that, but I'm very, very positive that this will be good for the CFD.
Great. Well, you're very lucky to have such a machine for one university. This is something that we do not have in the UK, I'm afraid.
Well, technically, it's not for the university. It's technically, it stands at KTH, but it's part of the Swedish national infrastructure for computing. So it's actually shared between the universities. But you have to, even though we're at KTH, we have to apply for it centrally and then to a committee, which then gives out the computer time. But
great. Thank you. Right. Let's talk about well, exascale computing. And my first question, I mean, you partly already answered that, but as a scientist doing CFD, when did you start thinking of, okay, we need to make our flow solver ready for, let's say, maybe not exascale computing, but for very large scale simulation?
Yeah, I guess that was what I mentioned before, when we realized that we can run on not just 16 processors as we perhaps did before, but on 1,000, 2,000 processors. That was, I don't know, 15 years ago, perhaps. But we also realized something else, and that is that it is, of course, very difficult to maintain a code that is very parallel, that you need to adapt for new architectures all the time, like now when you need to go from Intel to AMD, perhaps. This is very difficult, and it's difficult to get funding, and therefore we also then at some point needed to realize that perhaps we should also change our code base to use a code that also other groups are using. So not going away from this model that one professor, one research group, one student has one code and then they develop that, but rather to more community code. That was then also our decision to actually transition from our own codes to NEC 5000, which is a community code based on the spectral element method, and originally developed at I guess MIT and then Oregon and then the University of Illinois by Paul Fisher. And we then decided that was also around 2010, so maybe 10, 15 years ago, that we wanted to buy into that environment, let's say, and develop those things that we need to, which then run on top of the actual code. So I would say when you asked me about when we started to think about high as a large levels of parallelism, that was when we then also decided to actually go with NEC 5000, which already at the time was running on 100,000 processors, and now these days, of course, it's millions of processors that NEC 5000 can handle.
So yeah, so I wanted to ask you, so I believe the methodology behind NEC 5000 is, you think, possibly a good strategy to efficiently use supercomputers. And I want to ask you, are you happy with your choice, the choice that you made like 10 years ago to go with NEC 5000?
Yes, I think so. Of course, I mean, you always have, I mean, each researcher or each group perhaps has some own kind of opinions and preferences when it comes to discretizations, codes, and of course for us, coming maybe more from the fundamental side, maybe also transitional side, when you want to look at transitional flows, where the idea of high accuracy, high order has always been an important thing historically seen. That was, for instance, for us something that we just wanted, you know, a spectral code, because we thought at the time that this is one of those principles that we don't want to go away from. And of course, nowadays, I guess one can argue, you know, is it necessary to have that high order if you just do a turbulent flow, maybe doing, you know, a quasi-DNS or ILES, whatever you want to call it. Is it necessary to have, you know, around the 10th order, or would be a second order code be sufficient? But I think the flexibility that we have with NEC, that we can actually run both and more engineering type of simulations, but at the same time, the same code base with the same post-processing tools, we can run transitional flows where we have tolerances of 10 to the minus 14 for, you know, divergence, for instance. I think that's also something that is important for us, that we don't need to maintain knowledge, expertise on different codes. So yes, I think the choice of code is absolutely for our purposes is very good. But again, I'm not saying that NEC 5000 or the spectral element method is now the solution for everybody or all the CFD groups. For us, I think it has been a very good choice.
Great. So I guess in the last few years, you have invested a lot also in developing the capabilities of NEC 5000. And I think it will be good if you can tell us what are the more recent development or new capabilities within NEC 5000 that you have contributed to.
Yeah, I mean, we started out with stability type of methods, adjoint methods, optimization methods for NEC. But I guess the more recent additions were kind of also motivated by the transition to exascale, or by maybe not exascale per se, but the idea of being able to run larger and larger cases. And we realized that, of course, meshing and identifying, you know, what a good mesh is becoming a challenge. And if you think of more complex geometries, you don't know where to put your grid points, and that was then one thing that promoted us to actually start to look at adaptive meshes, error indicators, trying to identify how to build an optimal mesh, which is then suitable and for a specific calculation. I guess that's one of the main contributions that we worked on and still work on, is this coupling of NEC 5000 to an adaptive method, which we can then also use with hanging nodes. So we can then refine our mesh wherever the grid points are needed. It's not an easy thing to do, but I mean, we've come some way. We're not at the end yet. The other aspect is also what I mentioned before with GPUs. You know, maybe 5 years ago or so, it became clear that GPUs will come, so that there's no way of avoiding it. So we started at the time our GPU version, and it actually turned out that it's not the only approach to use accelerators for NEC 5000. There's also another approach which is done in the US as part of the exascale project in the US. We tried to kind of balance also the user experience in some sense. So namely that we try to not change the code too much, so that the existing users can still use their previous files and so on. So we then first opted for an open ACC way of including GPUs. Now we translate that to OpenMP, but I think that branch of the code, so the OpenMP, I guess now branch of the code, that's also one of our recent developments, where we're also still working on to be ready when then our Dardel or other accelerated computers come online. But I think it's these two aspects, which in some sense are both motivated by exascale, by being able to running bigger simulations.
Great. And I also see, one of your recent publication about using spectral element methods, so I believe NEC 5000 on field programmable
Yes.
gate arrays, FPGAs. So can you tell me a little bit more about this?
Yeah.
Work?
I think it's a very interesting work, and it's maybe something that we started recently, namely to collaborate much more with the computer science department, or the HPC department that we have at KTH. It really started from it was an idea from their side that we could see, okay, could we build a custom architecture that using these FPGAs to mimic or NEC 5000. We then realized that maybe we should not go with NEC 5000, but again, this mini app that I was mentioning before, NEC Bone, which in some sense encodes the main steps of the algorithm. And well, we had a very skilled PhD student that then started to implement that and transferring it. It was not easy, and it's a very difficult environment, I would say, to develop code on these FPGAs, because if you compile the code, it takes you, may take you 24 hours to just compile the code. And so that means you don't want to do that too often.
Yes.
But he was very skilled. He could actually then build this architecture and also do some modeling, performance modeling in existing cards, in future cards. But I guess the conclusion is, if one wants to put it like that, maybe right now it's not a choice or a method of choice to do so. But if one could convince some of these card manufacturers to actually change a little bit their setup, then one could build an optimized FPGA, which then could actually be performant or equally performant as graphic cards. Of course, whether this will happen is maybe another question, but at least as a test case, it shows that in principle, yes, it could be done, not with the existing hardware. So I guess for now, if you really want to do production runs, I guess we have to stick with either CPUs or GPUs.
Good.
Of the shelf.
Thank you very much. My next question is a hypothetical question. So if tomorrow you have access to a big supercomputers, or exascale computer, let's say, what will you do with it? I mean, there's a lot of discussion about, I'm just going to increase the Reynolds number, or I'm going to have a bigger domain, or more complexity, or I will run the same thing but much faster. What's your view on this? What do you think you will do with exascale computers?
Exactly. I mean, that's the important question. I mean, and then as you just said, I mean, the typical answer would be, let's just double the Reynolds number, and then the case is 10 times more expensive. And I believe that answer perhaps was a good answer up to maybe a few years ago, particularly when you think of channels or pipes. You could still do that, and you could get something new. I think it has become a little bit. It's maybe not so relevant anymore. I think the important aspect now, and also that's kind of what we are doing and trying to push, is to go to slightly more complex geometries. And what I'm mainly thinking about here is kind of curved surfaces, pressure gradients, maybe slide separated flows. There is, I guess it's a case that has been promoted by Boeing recently. There's kind of this a slender bump on a flat surface, which is one of those cases which could really, if you have good reference data, could help turbulence modeling quite well. So I guess it's cases. It's on the one hand, it's cases like that when you can really do what we call a hero run, in the sense of a very big run, which would be relevant. I mean, On the other hand, I think there's other aspects where it's maybe not so much the size of the simulation that matters, but including more aspects that make the simulation worthwhile. And there, of course, there's many things in multi-physics cases, particles, and so on, which is not my area of expertise, so I'm not going to say something about that. But I think one area where where we would need to have a lot of development, code development, would be in the area of UQ, so uncertainty quantification. And I think that's very quickly becomes very expensive if you want to have a certain number of uncertainties in your simulation. But I think the potential outcome, so that you get error bars suddenly on your results, I think that's one of the areas what you could do with a bigger computer. So not so much just increasing the Reynolds number. I think there we have reached somehow an end of where it's still giving you return that is reasonable. Although of course I like big simulations, and I've kind of been part of this game, let's say, before, but I kind of try to stay away of it.
Very good, thanks. That's why there's no new turbulent boundary layer, zero pressure gradient at a very high Reynolds number.
Yeah, exactly. I mean, I think it's not really what one should do. I think we have the Reynolds number we need. Yeah. Rather doing one with error bars, or something like that. That's much.
Great. So it looks like your research group is more or less ready for exascale computing, but I wanted to have your opinion in general about the turbulence community. Do you think people in our community are ready for exascale computing, or you think there is still a long way of software development for the majority of people?
I think that's a very good question, and actually I would say that there's a lot of people in our community that are very ready. They're probably more ready than we are, but I also believe that there's maybe a number of people that are not ready at all in our community, and I think it has a little bit to do with the fact that traditionally it seems that we have not had so many community codes. I mean, there are of course a few. I mean, NEC is one. Impact Incompact 3D is another one. There is of course OpenFoam, but I think to a large extent there were individual groups having their own codes, and they were kind of running that with great success for a long time. But I think now some of these codes have come to an end with this transition. So therefore, I would say perhaps now more and more people will need to switch to one of those community codes, which of course is maybe good, because then one can actually focus the code developments on a few codes and making them running exceptionally well. But it may pose some challenges on existing software that maybe some people have. But I guess at the same time, in a few years, I would guess that also the compilers or the tools or the libraries that people have access to will also become better, so that maybe some of these older codes can then be transitioned again. But of course, I guess there would be now it's a window of opportunity of codes that are ready to use these new accelerated machines, and whether it's the KTH one or some of these other European ones, or Archer 2, or where you could perhaps then go and get a lot of computer time, because it may not be used by everybody. But
good. Thank you. I have a couple more questions. This is a question that I like to ask, is if there is one thing that you could change in high performance computing. So I'm mainly thinking about hardware, like to suit better your need. What would you change?
It's a difficult question. I guess I guess one aspect which we have struggled at times is, I mean, we need to, how should I put that? We want to run our, I mean, we want strong scaling in the end. That's what we would like to have at the end of the day, which means we would be able to run with as many processors, or as few nodes as few grid points per node as possible. And of course, that's something that it's of course difficult to implement. It's difficult to say what exactly one needs to change. But if this would be my wish, that's perhaps where go. It seems to me that the initial tests now with this AMD EPIC processor, they indicate that somehow with the memory layout that they have, it is actually such that we can get quite low. We have, for instance, if you just look at what level you get half of the peak performance or half of the fastest performance of the code, that turns out that there's just one element per core. So that's very, very little, and that's more that's better than it used to be before. So it seems that actually the processor industry has kind of made in particular memory structure better, and the whole the cache and hierarchy is better, that it's more suited for HPC calculations. But apart from that, it's difficult to say. Of course, I mean, for a long time it would have been we need to run double precision and all of that, but these things are kind of solved. Maybe more on the wish list would be on the software side from the hardware manufacturers, and that is what type of programming languages are supported on in particular accelerators. And of course, now we have seen a number of these hardware specific languages or vendor specific languages, which of course I mean, I understand the business model in some sense, but of course for us as a scientist to switch from language A to language B, and it's of course a little bit difficult, but perhaps difficult to change. But I guess that's
right. One last question is, so we are talking a lot about exascale computing, and I wanted to know your view on what will come next. In particular, well, in the last few years, we have seen, GPUs are becoming faster with more memory, less energy requirement. So there's an incremental improvement of performance. Do you think this will continue like this, or do you think we are going to face like a hardware revolution of some sort with brand new technology, and we will have to redesign everything again? What do you think?
Actually, I have to be honest, I do not know. I really don't know. I hoped that we could, maybe 5 years ago, I kind of hoped that we could avoid the whole GPU business. I guess that did not happen. I guess the really new challenge would then be eventually something on this quantum computing thing. I don't know whether there's anything reasonable or useful for us there. I really cannot answer. I hope that what we invest now can be used for a number of years, maybe decades to something like that. In the end, it has been amazing how long MPI could have been or could be useful. The standard way of just message passing, it survived a lot of different trends, and I kind of hope that maybe the way that we program now can continue in the same way. But I guess another thing that one may think about is also completely new algorithms. That's maybe less on the hardware side, but on the software side. And of course, aspects there are machine learning, of course, that everybody's talking about that. But can we invent some algorithms that actually are based on that in some way? Can we use those to make certain predictions, derivatives in a better way, or wall models, or things like that? That of course could be one aspect. Or completely different algorithms in the sense that do we want to completely switch, for instance, to compressible codes to avoid the way that we need to treat Poisson equations and so on? Could that be a solution? I guess so far, for instance, the last point, so far it was not necessary, but maybe that's something which will come. But on the hardware side, it's difficult for me to predict.
Great. Thank you very much. I think I lied to you because I have one more question that I forgot to ask you at the beginning, and I think I always wanted to ask you this question is, how is your Swedish going?
My Swedish? It's going well. I'm teaching in Swedish, and
so you are teaching in Swedish?
Yes, yeah.
Wow.
I think it's okay. The the students don't complain so much. Of course, at times I'm using I mean, I'm inventing words which sound Swedish, but apparently are not. But it kind of works. But maybe that was another aspect why Sweden is, of course, very nice for foreign people to come, because very quickly, I mean, very quickly, the working environment is in English, so you can actually survive quite easily as I mean, using English. But
good. I didn't know you were teaching in Swedish. I was assuming you were teaching in English, so you know.
No, the bachelor is in Swedish, so one has to.
Wow, good. Well, thank you very much, Philipp, for your time, and it was really nice talking to you. And we, of course, wish you all the best for your future endeavors and future research project. That's all for us. As usual, you will find the recording of the podcast available on the UK Turbulence Twitter account, and all the links will also be made available on the UK Turbulence website. So thank you very much, Philipp, again, and thank you everyone for listening to this podcast, and hopefully we will see you soon for a new episode.